Okay, so we got past this slide. Preparation of alcohols, that's where we're at. So how do you make an alcohol? We talked a little bit, but there's a whole bunch of ways you can make alcohols. From alkyl halides, which we're showing here, you could do it by substitution reaction. Okay, so substitutions, we typically think of SN1, SN2, but there's all kinds of ways that we can do this that are not straight SN1, SN2 reactions. Well, we'll start with the simplest ones, right? You can use a primary alkyl halide and sodium hydroxide, and you get a nice SN2 reaction to form the alcohol. You can do a tertiary alkyl halide. This is an SN1 process because what will happen is this is a bad nucleophile. This is sterically hindered, right? You can't get a backside attack. And so what ends up happening is a carbocation forms. And once you have the carbocation, that is, let me make a little note here. Once that leaves, that's a two-headed arrow. Once that leaves, the carbocation's there, then the OH, the H2O can come in, attack, right? And then you form your alcohol. A couple of steps in there, but we covered all that last semester. Okay, why can't you use sodium hydroxide down here with the tertiary? Yeah, because for alkyl halides, the reaction that's fastest, right, depends on the structure of the substrate. So if it's primary, it's always SN2. But if it's secondary or tertiary, you get elimination byproducts. Okay, so you'll end up, if you did OH here, just as a reminder, you'll get E2 reactions. And so you'll end up with things that look like, probably something that looks like that. Okay, so that's the kind of thing that you're trying to avoid. And then that leaves secondaries. And in secondaries, you have to be careful of rearrangement to like a tertiary carbocation. So if you remember, once you form a carbocation, if you form a carbocation at a secondary carbon next to a tertiary carbon, that is, you do something like, right, then you'll get a rearrangement reaction, and so this hydrogen here migrates over to that position. We call that the hydrate shift. So there are better ways to do for secondary alcohols, and we learned a bunch of them. One that's good is this one if you don't have to worry about rearrangement. Dilute sulfuric acid and alkene, right? It's a hydration reaction. Add water, right? And you can form an alcohol. But if you have to worry about rearrangement, then this oxymercuration demercuration reaction is what we use. And if you remember, like the Y, right, the intermediate, the intermediate for that looks like something like this. This HGAC, and that formation of that cyclic intermediate prevents the rearrangement. Okay, so carbocation mechanisms, this top one, this is one of those cyclic intermediates. And then if you want to do an alcohol on a primary carbon or at a less substituted carbon, do the anti-Markovnikov addition. Does it say that anywhere in here? Yeah. But if you want to do anti-Markovnikov addition, then what you do is you do the hydroboration reaction and it adds at the less substituted carbon. Okay. So there's a bunch of different like tools, ways that you can make alcohols. A couple of different ones for secondaries, simply because you might want to avoid rearrangement or you might not care. So it just depends on what your needs are. Okay. The other nice thing about this reaction is in terms of like reaction conditions, it doesn't require sulfuric acid, and so a lot of functional groups are sensitive to acid, and so we try to avoid those kinds of things. Yeah?
In the book, it said that instead of doing hydroboration oxidation, you could do an anti-Markovnikov addition
And a substitution for a primary? Yeah, you could do like, okay, what's the anti-Markovnikov addition that they're talking about? HBr with peroxide, yeah? So yeah, you could go like this. If you do HBr. It could be ROOH. I just and the peroxide actually. Sorry. Let me do it like I think it's normally they do something like this, or they actually. Sorry. Roar. What? Has little eyes? Oh, it does. Oh, look at that. Now it's alkyl halide face. That's what I have in the morning. So I did this morning. I was really never mind. So MCP. That's a peroxyacetic acid. So any peroxyacetic acid. Anyways, sometimes that's used. Questions? I just do R, eyeballs, R.
So you use the proxy acid to form a non-oxide? Is that what you use?
Oh, yeah, that's right. Yeah, it's used for peroxide. I think you can use any peroxide there, though.
To make an epoxide?
No, to
Install
be the radical reaction.
Oh.
I'll look at that, though. For some reason, that came up in my head, but maybe I was just remembering wrong. I'll blame old age. Other questions? Besides old age questions? Okay. Okay, so there's another way to produce alcohols, and that's from carbonyl groups, so aldehydes or ketones. Okay, so we can do reduction reactions. Before we do that, we're talking about oxidation states. Did I do the oxidation state thing with you guys yet? We talked about some of that?
Yes.
Okay, good. So then I was kind of past that stuff, but it's good that I went back through it, just to review. We'll just go to this slide then. When you do oxidation states, right, carbon, hydrogen, carbon's more electronegative. When you do oxidation states, you just count. Like, since this one's more negative, you go -1, -2, -3, -4. This is a -4 oxidation state. If you go on to this side, right, this is oxygen. It's double bonded, so it's +1, +2, +3, +4. That's how you do the oxidation states. When it gets mixed, like it is here, then you would say -1, then +1, +1, and +1, so it'd be a total of +2. Okay? So basically, for organic chemistry, when we do oxidation states of carbon, it's really easy. You just have to remember what's more electronegative than what, and you do the calculation. Probably ask you on a test, for example, what the oxidation states of these two things, and this is an oxidation reaction or reduction reaction. So if I go from here, oops, I did it again. To there, that's an oxidation reaction. You should look for an oxidizing agent. And if I go from here to here, that's a reduction reaction. You'd have to look for a reducing agent. We don't know the reducing agent for that one yet, but we'll learn that might learn it in this chapter, maybe the next. I don't know. It's not very hard, but there's a reduction reaction to do that. So oxidation or reduction? What's the title say? Yeah, it's a reduction reaction. You could do that by calculating the oxidation state for this carbon versus this carbon. And what you'll find is that this one is +2. And remember, if you're more electronegative, you get a negative charge. If you're less electronegative, you get a positive charge. If it's a carbon bonded to carbon, 0. Yeah. And then here I have carbon 0, right? Oxygen +1. Is it +1? No, because there's a hydrogen hiding. Yeah, there's hydrogen here. So this one's actually 0. So this is a reduction reaction because I'm taking the oxidation state from +2 to 0, and so you need a reducing agent. So let me throw something out at you first before I get into the meat of the topic. I want to make a little whiteboard and do this. I kind of like introducing the topic like this. I have a compound. I don't know what to call this compound. Actually, let me do a bigger one. I'll do one like the one they have in the book. I have that. Okay. And I do hydrogen and a catalyst. So catalyst like palladium. Okay. The outcome of that reaction is a reduction that gives me that. Okay? So what happened? All the pi bonds were reduced, right? Now, in lab, we use sodium borohydride. If you had done sodium borohydride in this reaction, you would have gotten that. So what happened? Only one of the pi bonds got reduced, right? And only the pi bond involving the carbonyl. So inherently, what that tells us is there's something different about the two pi bonds. So I kind of like to do a little quick comparison so we can talk about it. That pi bond versus that pi bond. What's different? What's that? Oxygen, yeah. And this is carbon-carbon, right? So this is carbon-oxygen, and this is carbon-carbon-carbon. Okay, in terms of physical characteristics or chemical characteristics or properties, however you want to think about it, what does that cause to be different? Big electronegativity difference, so charge distribution. So this one is very polarized, all right? And this one is nonpolar. In fact, this partially explains why sodium borohydride is selective for carbonyls and aldehydes and ketones. Because if you look at the structure of sodium borohydride, you have a negative charge, you have a boron. It's got 4 groups on it that are hydrogens, like this. The formal charge, negative formal charge sits on the boron, right? Okay. In terms of electronegativity, hydrogen is more electronegative than boron. Okay? How do you know that? You looked it up. There's not like a good way on the periodic table to say where hydrogen fits, but it turns out it fits right between boron and carbon. Okay? So because hydrogen is more electronegative than boron is, remember we talked about bond cleavage, and when a bond cleaves, which way do the electrons go if the electronegativity is different? To the one that's more electronegative, right? So that's how we get our cations and anions in general chem, like sodium's +1 and oxygen's -2. Yeah, that's how you break, actually when you break the bond, unless it's being attacked by a radical, when it gets attacked by a radical, you usually have a splitting of one electron going each way kind of thing. But so what'll happen here is when you take this borohydride and you put it in solution and it reacts, I'm going to put R's up here because you could put any functional groups, like the R groups can be used to modify the reactivity of the boron and the hydrogen, right? When this bond breaks, it breaks like that. And that the hydrogen stays with the pair of electrons, and the boron gets left alone with an incomplete octet. Okay? So, this transfers the way we like to, well, okay, the way I like to think about it, it transfers as a hydrogen and a pair of electrons, which is hydride. That's the name of that substance. And we can make hydride in lots of different ways, but it's essentially hydrogen acting like a nucleophile. Okay? So if you look at this bond and this bond, right, this is nonpolar, right? So the hydrogen won't attack it because there's no preference for it to attack it. There's no charge on that double bond. But on the carbonyl, right, there's a positive charge here. So when the hydrogen comes in as a nucleophile, it's going to attack the carbon because it has a positive charge. And that's why like sodium borohydride and lithium aluminum hydride and a whole class of compounds that are like those attack the carbon and reduce carbonyls rather than CC double bonds.
What about we learned in alkene reaction,
Mm-hmm.
the same reaction reducing alkenes, right? In chapter 9.
Yeah, but that was using H2, right?
That was using exactly the same reaction. NaBH4, HgOS2, and water, right?
Say it again?
NaBH4, water, and HgOS2.
That makes an I think you mixed it NaBH4,
You're talking about
oxymercuration reduction.
Yeah.
Yeah, so the order is for that one is oxymercuration, and then the second part is the reduction step,
Yeah.
right? And you have this mercury oxygen carbon bond, and that hydrogen gets transferred and breaks one of those bonds. The rest of it's not really clear, like how the mercury actually completely gets displaced off the structure. It's like it's in 28A, the mechanism. You guys remember the mechanism for that? Then a miracle occurs, because we're not really exactly sure how it happens, so I just say then a miracle occurs, and we ignore the rest of that. But I could go over that with you, like how we did it in the first semester. But yeah, sodium borohydride is being used to transfer a hydrogen and a pair of electrons to displace the mercury. Okay? All right. Yeah, so standard couple of ways to do alcohols via reduction then. Hydrogen gas, right? And platinum and palladium or nickel metals, nickel catalysts. Those are, if you think about the surface of the metal, nonpolar, it absorbs the pi bond, and then the pi bond gets, and the hydrogen, and those bonds get broken, and then the hydrogens transfer on. There's a stereochemistry associated with this kind of reduction. You guys remember the stereochemistry associated with this kind of reduction? Syn addition, because it's on a surface, and both the hydrogens have to add from the surface, okay? Sodium borohydride reduction looks something like this. Here's the mechanism, right? There's the overall. And the solvent is one of these. It can be any alcohol. Okay. So, aldehyde or ketone, okay? Sodium borohydride. This is the hydrogen going along, being transferred with the pair of electrons, right? So that breaks the pi bond, and you end up with this oxyanion. And all that this needs to do is from the solvent, one of these things, right, proton transfer, and then you end up with your product. It's a very simple mechanism. Doesn't do this on alkenes simply because the alkene's not polar, okay? Not reactive enough to be reacting with it. Questions about mechanism? There's not really like a syn or anti-addition to this, because this gets added and then that gets added in a separate step. Okay. Now, a little side note. Periodic table, right? There's boron, and there's aluminum. Okay, so which one's more electronegative, boron or aluminum? Boron, okay. And so, but hydrogen's more electronegative than boron. So that's the partial negative, that's the partial positive charge. what does that mean about the aluminum and hydrogen bond and how polar it is? Is it more polar than the dot bond or less polar? It's more polar because aluminum is less electronegative, right? The thing about that trend on the periodic table, right? Electronegativity increases going on the way up. So this bond is more polar. So here's the thing. Sodium borohydride, you guys used that in class, in lab. So it's a relatively mild reagent. You used it last semester. It's like the first real experiment we did. And when you're using it either this week or you used it already last week. Aluminum hydrides are much more reactive because the polarity of the bond is much larger. The polarity difference between the hydrogen and the aluminum is a lot bigger. So everything you do with sodium borohydride, right, can also be done with lithium aluminum hydride. So exact same kinds of things, okay? But you notice something that they did here. They did lithium aluminum hydride. You know, that's actually kind of hard to say. But anyways. And then the second step is they add water. Right? So the first step is for the hydride transfer and the reduction of the carbonyl. Second step is for the proton transfer. You can't do this together because it blows up. Right? Because lithium aluminum hydride is a lot more reactive than sodium borohydride. So if you try to do them like in what they call a one-pot synthesis, where you just dump everything into one pot and you stir it around and out comes the product, okay? If you try to do that with this, you're going to have a lot of problems because the lithium aluminum hydride is such a strong reducing agent that it reduces any protic solvent. So any solvent that has hydrogen on it, it'll reduce it, and then it's not available to do the reducing of the carbonyl. Okay. So what I mean by that is the side reaction is that if I have protic solvent and then I put aluminum hydride in here, and I'm going to put the H down here because it's easier to draw, and then there's a bunch of stuff there. It'll just do that. And then what you end up with is a lot of heat, and you end up with hydrogen gas. Okay, so that's why you can't use a protic solvent with lithium aluminum hydride. In fact, there's a lot of organic reagents that don't like water. But otherwise, it's exactly the same as sodium borohydride.
Doesn't aluminum ion mix a weak acid in water?
Yeah.
Wouldn't that become a protic solvent too? Well, wait, no, it's not.
But I don't have aluminum ion.
Oh.
You're thinking aluminum 3+. Metal cations, right, will coordinate with water and then release a proton and make the solution acidic. That's not this.
Oh, okay.
Because that's not aluminum ion, that's aluminum hydride. Yeah, different. But good to get that thought out of your head, so it's good. Vent the thought from your brain. Okay, so standard reaction, sodium borohydride, lithium aluminum hydride. Yeah, so how can lithium aluminum hydride be used with water? If it reacts with water, it can be used if it's the second step. Right? And so typically what you do is you take the reagent, and the solvent is usually like an ether, aprotic solvent, right? So ethers are, just by review, remember the bat molecule? Diethyl ether is pretty common. And then in the second step, when they add the water is actually used to protonate the alcohol that's formed, because in the first step you get the O-, and it's used to get rid of any of the excess lithium aluminum hydride. So typically what they do is these reactions are run at very cold temperatures, like as cold as you can get, like minus 78 degrees Celsius. And then when it's still cold, they add a protic solvent to it, and then they stir it like crazy, and then they let it warm up to room temperature. Because as it warms up, the water will neutralize, or they say quench, the reaction for the lithium aluminum hydride. Okay? But typically they're mixed together very cold and then allowed to come to room temperature. And then you don't use a lot of excess lithium aluminum hydride. Okay. So why do we have two different things, right? Turns out lithium aluminum hydride is used for a lot of things that sodium borohydride isn't reactive enough for. Oh, yeah, sorry. Side note. So sodium borohydride, lithium aluminum hydride could be used in this reaction to do this, and hydrogen would do both like that. What if you, let me ask a little follow-up question. What if you wanted this? 7-membered ring, unfortunately. I hate 7-membered rings. What if you wanted to make that? All right. Well, there's not a way directly from this. Well, there are ways, but we don't know them yet. The answer is simply just oxidize that. All right. So in lab, we used like chromate, but oxidizing agent here. So chromates can be used. Bleach can be used. There's a number of different things that you can use to oxidize that. And we'll talk about those reaction mechanisms today, too. All right. This is a little side note. Most of these reagents can be made more or less reactive by having different functional groups, by like using inductive effects to make them more or less reactive. Okay. Electron withdrawing groups tend to make them more reactive, and electron donating groups tend to make them less reactive, if I remember right. But that's a little side slide. Okay. Now, the other thing and that lithium aluminum hydride is really good for is reducing carboxylic acids and esters, and a couple other functional groups, actually, to primary alcohols. Okay. And so here, right, lithium aluminum hydride, first step, second step is water. It's about 2 moles of lithium aluminum hydride for every 1 mole of this. It's a little bit more than that, but on this one's probably closer to 3, but you'll end up with the primary alcohol. This one's closer to 2 moles of lithium aluminum hydride. And what you'll end up getting is this as an alcohol, right? And the R group as an alcohol as well, primary. Mechanism, pretty much what you might expect, so we'll go through it real quick. This is the easiest one to do, so we'll do this one. All right, I have an ester. Again, this bond is, right, this carbon is very positively charged. What makes it a little bit tricky is this pair of electrons. There's resonance here, right? So the positive charge here is not as great as you might expect it to be, and that's why sodium borohydride doesn't react with it. Okay? Because sodium borohydride expects a positive charge. Turns out by resonance, there's a lot of negative charge distributed to this point, and as a result, it's not as reactive towards the hydrides. So anyways, aluminum hydride transfers a proton. You get this, and geometry-wise, right, this is trigonal planar. The groups have a lot of distance between them. This one's tetrahedral, and so the angle between the groups shrinks, and that creates strain. Okay? So what happens is, because of the strain, that we call it the tetrahedral intermediate, because the tetrahedral intermediate has strain, is it brings this bond and closes it to a carbonyl again, and then this leaves as a leaving group. So off it goes, right? For those of you good at visualizing mechanism, what functional group does that leave you with? Leaves you with an aldehyde, all right? So that leaves you with this. And guess what? Lithium aluminum hydride's in the solution already, so it reacts with that and converts it into a primary alcohol. So now you have this, you're back to this kind of reduction. It's an aldehyde, right, converted to a primary alcohol. That's the second equivalent of lithium aluminum hydride in the reaction. So this is where we were at, all right? So going to the next slide, the aldehyde that's formed picks up a second equivalent of hydride, a lithium aluminum hydride. And then you add the water and heat it up, and it picks up the proton. There are 2 moles of hydrogen added to this carbon, right? 2 equivalents. In terms of reversibility, all right, I got something weird in my teeth. Right? In order for this step to be reversible, you'd have to be able to kick off H minus. H minus is super reactive, so it's not going to come off. Hydrogen's a very strong base. Hydride's a very strong base. So you go this first step, that's not reversible. You do the second step to here. It's reversible between this slide and the last slide. Right? So if I have, it's such a bad place to break the slide, but in terms of reversibility, I have this. So that's a reversible step. This is not reversible, and then the proton transfer is a reversible step. So basically, once you start this reaction, because of where the irreversible steps are, the hydride transfers are, it just drives the reaction to the end and doesn't go back. It's not something you can easily go back from.
Why doesn't the reaction stop with the aldehyde?
Oh, because you have more lithium, you do it with an excess of lithium aluminum hydride. Aldehydes are very reactive, and so it just picks up a second hydride. So if you think about like this versus like that, just generalized, right? This carbon has a positive charge, right? But part of the positive charge of this is stabilized because this oxygen, there's resonance. And so it's an electron withdrawer and an electron donator. So when you try to do like borohydride reduction to this positive charge is not big enough to pull the hydrogen out. Okay? But when you do aluminum hydride, it turns out this bond is polar enough that it can do that first step of the reaction. Okay? So you do that first step, and you end up with like that, right? Turns out this doesn't have the second oxygen donating electron density back. It turns out it's more reactive. And so as a result, you make this, it goes to this collapses, and this group leaves. Okay? So you're like this now, and that's more reactive. So the second equivalent actually adds faster than the first one does. All right? All right, I lost my teeth. So this is fun. Let's predict what you get when you add lithium aluminum hydride or sodium borohydride to this compound. So, for sodium borohydride, what functional group will react? Just a ketone, right? So that guy will react. And then for lithium aluminum hydride, I have both, right? I have this, and I have this. Now, when you think about how this is going to work, you're going to break this bond here, right? And both sides will become primary alcohols. Now, personally, when I do these kinds of things, I almost always have to go through the mechanism to make sure I don't screw it up. But I think most people, they're happy knowing, oh, this is what happens. So, but I always have to work through a mechanism in my head. Okay. So for sodium borohydride, for the first case, that is for this, the product is pretty simple, except for you got to draw a 7-membered ring, which I think I've told you guys in the past. I really hate doing that. So I'm going to draw a really horrible 7-membered ring and ask for forgiveness from the organic chemistry gods. And I get that. Plus, Docere is not real happy with me right now. Right. So for lithium aluminum hydride, I'll break this bond that's up here, and this will also get reduced to an alcohol. So what I'm going to do to make my life easier, or maybe I think it's to make my life easier, I'm going to number this 1, 2, 3, 4, 5, 6, 7. And I'm going to draw a heptane. And then this is 1, and this should be 7. See, let me double check. 2, 3, 4, 5, 6, 7, right? 2, 3, 4, 5, 6, 7. All right, that's close to right. This is 7 here. So what are the functional groups that I'm going to have? Well, on 2, I'll have an alcohol. On 7, I'll have a primary alcohol. What am I missing? Double bond between 5 and 6, so I'll go 1, 2, 3, 4, 5, 6. There's a double bond there. And then on 4, I've got a 2-carbon chain like that, right? 2 carbons. And then what's on that? Primary alcohol. Like that. Okay. It's very helpful if you just number the longest chain continuously in the molecule and then just draw that long chain out and then plug the functional groups on where you know they're supposed to go based on numbers. And as a reminder, I do post these videos. So it's Dr. K's Chemistry. And it's on YouTube. And I posted all the videos from the last 2 weeks. Is this 3rd week already?
Yeah.
Good God, really?
Oh, I guess 15 more minutes until the final.
It's a good thing I took Lamaze classes. Well, I did. Like a bunch of times. All right. Okay, any questions about this? What went on here? All right, so we'll move on to diols. Yay. Because if it was fun making 1, it's even more fun making 2. That's probably not true. Okay. Well, we actually know how to make a diol one way already, is like the reduction of a cyclic ester. That's not covered in these slides, but that's just what we did just now. Like this, the reduction of a cyclic ester, often known as lactones, will produce diols. Okay. But the other way is just from diketones or dialdehydes. So if you have either sodium borohydride, lithium aluminum hydride, or hydrogen, so all of these will do the exact same thing, all right, you can form a diol. But you have to have 2 ketones. That's almost like cheating, right? You got 2 ketones. Although they don't cover this, so I'm going to throw in, like, why would they talk about this? Because it's not actually as uncommon as you might think. So how do you make a diketone? Yep. O3 and 2-DMS. That's a D. Sorry.
There was something similar to that on chapter 12 onward.
Okay, good. I couldn't remember if it was.
Yeah, it's split cyclo.
Yeah. Yeah, so you do that, and when you do that, you basically think of the molecule being split like this. And you put oxygens at the end like that. And so in this particular case, I use 6 carbons, so it'll end up being a dialdehyde. But then if you do the reduction using sodium borohydride, lithium aluminum hydride, or hydrogen and palladium, then you'll end up with a diol. So it's not an uncommon thing to see that you have a cyclic structure with a double bond in it. You do ozonolysis, it cleaves it off into either a dione or a 2-carbonyl functional group molecule. Okay. And then, yeah, once you have alcohol functional groups, you can do all kinds of funny things, but we'll talk about that in a little bit. Another way to make diols is the oxidation of alkenes, either using a peroxyacetic acid and acid catalyst, or using osmium tetroxide, and NMO is the catalyst for the reactions. This is catalytic amounts of NMO. That's the catalyst, sorry. And NMO is kind of like the cofactor that goes along with it that helps to regenerate the reagent. Sorry, that's a biology term, but it seems to be so much nicer. All right, so if you remember, too, and the intermediates, all right, this one involves an epoxide. And then when the second hydrogen comes, or second oxygen comes in, it's SN2. And that's what leads to the anti sort of stereochemistry, is because the oxygens will end up being on opposite sides of the structure in terms of stereochemistry, because it's an SN2 reaction. And this one, in using osmium, it involves a cyclic intermediate. Something like that. And because this is formed in a concerted step, both these oxygens have to be on the same side of the pi bond, so they're either both in the upward direction or both in the downward direction on the ring. On this ring, it doesn't matter because it's symmetric, but if you had another functional group on here, it would matter. Okay, but the oxygens end up being added from the same side of the ring, or same side of the pi bond, so it's a syn addition. Okay. So, switching gears just a little bit. Okay, this is a whole area of organic chemistry that's very important, and it falls under the category of organometallic reactions. It's really slow. Network's lagging on me. I experimented with this at home, and it worked much better at home. Organometallic reactions. Probably the most well-known of these is the Grignard reaction. Although before the Grignard reaction, they actually did what are called organozinc reactions. And if you look into next week's lab, that's what we're doing. We're doing organozinc reactions. They were the first ones to be like discovered and used, but very quickly they found out that Grignard was a lot easier to work with. Okay, and it's an interesting reaction because what happens is you have to make the Grignard reagent from an alkyl halide. And it involves a radical reaction where the magnesium transfers one electron and breaks this bond here. And you end up with, at least speculation is it looks something like this. And then these couple. So what you end up happening is it looks like the magnesium's on the outside and then switches to be on the inside. We draw it like this because the electronegativity difference is something like, if I remember right, like 0.9 or 1.2 or something like that. So remember when we talk about like ionic bonds, right? It's not really ionic, but it's polar with a lot of ionic character to it. Okay. So the way we treat Grignard reagents then, this side's really positive. This side's really negative. And so a lot of times it gets drawn like this, which I am okay with. And it's a nice way to make a very nucleophilic carbon, so you can add carbon groups. Moieties is what we like to say, but I'm just say groups. You can add carbon groups to other functional groups. Okay. This is a nucleophile, so it can add to an alkyl halide and do a substitution reaction. It can add to a carbonyl, just like the borohydride transfer. A pair of electrons goes to the carbon of the carbonyl. It's used for all kinds of things to attach functional, like carbon groups to other carbon groups. Okay. If you do with a chloride, you get the magnesium chloride Grignard reagent. If you do bromide, the magnesium bromide Grignard reagent. Let's see. And does you can do the oxidation state, but it doesn't change. So it's not a redox reaction. Okay, so yeah, we treat, for example, it's known as phenyl magnesium bromide. We treat it really as a phenyl group of benzene ring with a pair of electrons to act as a nucleophile. Yeah.
For the exam, do you want us to show the mechanism for the magnesium?
Oh, no, because there's a lot of different ways that people say it happens. Yeah, I don't think it's that important. Yeah. It is another radical reaction, so it's kind of nice that we just did 11, and you can see how it's involved everywhere. But yeah, don't worry about the formation of the Grignard reagent. Yeah.
Just know the magnesium goes in the middle. Just magnesium goes in the middle.
Yeah, you have to know how to make it, though. That's, yeah. Okay, so, sorry. So, what? Hey, so again, Grignard reagent acts as a nucleophile. So if you imagine you have a carbonyl here, you can take your Grignard reagent, attack the carbon of the carbonyl again because this is the positive center, this has a negative charge, acts as a nucleophile, and then you end up forming an alcohol, which is why I think they stuck it in this chapter, but it's like so much bigger than that. But anyways, yeah. So you end up forming alcohols this way. It's similar to lithium aluminum hydride in terms of mechanism, similar to sodium borohydride. The other thing that you could do, and some people actually do this, they use Grignard reagents as bases because Grignard reagents, just like lithium aluminum hydride, are so reactive that there's any protic solvent involved, it will react with it, okay? So if you have the Grignard reagent, any water present, right? This pKa is close to 50. This pK is 15.7. Really favors the formation of the product. So when you use Grignard reagents, and this is one of the drawbacks, Grignard reagent reacts with carbonyls, okay, and it reacts with water. So experimentally, it's a real pain in the butt because you have water on almost every piece of glassware. So you have to take your glassware, you have to get it super clean, and then you know how you guys always take the blow dryer to it and heat it up, right? You actually have to stick it in an oven and bake it because there's a lot of water that sticks to the glass. And in order to make the Grignard reagent and have it be usable, it has to be what we say scrupulously dry. Okay? Scrupulously. Scrupulously. Yeah, right?
Can it pull any water molecules from the air?
It can pull water from the air.
So you have to use it in a vacuum?
No, you can use nitrogen. Some dry air, or dry air. But you can't really just use dry air because what else is in air? There's
CO2.
CO2, right? Carbonyl, right? CO2 is a carbonyl. You end up making carbox. If you take a Grignard reagent, actually, we actually used to do this one. I'm not doing it this year just because I'm not doing it this year. We would make phenyl magnesium bromide. And then react it with CO2. So I would go to the liquor store. I always just like tell people, "Yeah, I went to the liquor store today right before class, and I bought dry ice." They're always like, "What?" Yeah, I have to buy dry ice. And we make benzoic acid. It's a fun. You end up getting that actually, and then you add acid to it to protonate it. Anyways. Yeah, so if you have any CO2 in the air, so yeah, a lot of times when they do these experiments, dry air doesn't have that much CO2 in it. Usually you use like nitrogen or argon or something that's not going to have a carbonyl in it to react with it. So since we're not doing this experiment this week, and you see me at a liquor store before class, it's for a completely different reason. All right. And if it's right before your class, that should tell you something. All right, so some examples of Grignard rate. Methyl magnesium bromide, that's what this dude up here is called, right? Carbonyl, right? Put a methyl group there and you end up with a tertiary alcohol. Again, it's SN2, it's like an SN2 reaction. It's a nucleophilic reaction. It's not really SN2. It's called an addition-elimination reaction, or addition reaction. This is what happens when you have an ester, okay, excess methyl magnesium bromide. And you notice what happens? You end up with two equivalents of methyl magnesium bromide added. And you end up with a tertiary alcohol again. And the thing that comes off is this guy. Well, we should, to answer your question, draw a mechanism. So I'm going to draw the mechanism real quick. Generally, when I draw mechanisms, you're supposed to know them. So let's do this. I'm going to do okay. So I have ME and then MGBR. Man, it's really slow. And you end up with this. Like that. This is the tetrahedral intermediate that I talked about before. Okay. And this collapses, that's the term we use. So you have four groups, create steric strain. And when that collapses, methyl is not a good leaving group, right? pKa is way too high for like methane. So it's not a good leaving group. So, but the OMe can leave. So that's the methoxide leaving group. And then you end up with a ketone, and then a second equivalent of the methyl will add. Again, you get that tetrahedral intermediate, but in the tetrahedral intermediate you get for this one, there is no good leaving group. So you end up with this. And then the last step is usually something like HCl. We use HCl because what ends up happening when I'm going through this mechanism, you notice I didn't say anything about the MGBR, right? The MGBR actually stabilizes this negative charge and then sticks. And so in order to actually drive it off, we usually use like concentrated or strong, like 6 molar sulfuric acid, or sorry, hydrochloric acid. And that's enough to deprotonate this and kick the magnesium bromide off. And then it gives it a chlorine to pair with.
Isn't there a word you use?
What's that?
You use to kick down GBR?
Oh, HCl. I said, I started saying strong acid, then I ended up saying sulfuric acid. I mean, it could be used, sulfuric acid could be used too, but typically we just use HCl. What's that? Yeah, yeah. Oh yeah, so over here, that methoxide is part of a, like, can be like this, MgBr, OMe, or it can be just OMe minus. There's a lot of ways that it gets like in there. Oh, you do, but as your final product, generally speaking, you're shooting for the alcohol. And so you got to get rid of it. And that's the easiest way. Yeah, no. Yeah, it's a good question, though. So you end up with that. She asked, if you didn't hear, why don't you want the MGBR there to stabilize it? You kind of do. That helps the mechanism go along. But at the same time, your final product's an alcohol, so you have to get rid of it. Yeah, so it will take, see the MGBR that's over here? When that gets kicked off, it'll have a positive charge, so it'll pick up the chloride. Yeah. And then you usually have like an aqueous and an organic phase, right? And all the salts go into the aqueous phase, and usually all the organics go into the organic phase, so you can separate them that way. And sorry if I keep talking about lab and lecture, but like chemistry, it's really hard to separate lab and lecture because like so much of what you do in chemistry is about doing stuff in lab. So I just, huh? Why is it 2 different classes? Yeah, you really want to know why? Because that's what Fresno State does, and that's what all the UCs do. Yeah.
So if they fail one, you don't have to take both of them again.
Yeah.
It's helpful.
Yeah.
So it's a good thing. Yeah.
But then you don't have your labs to help pull up your lecture grade or vice versa, right? Some people are good.
Exactly. See?
Hey, just suck it up and get over it, okay? Ah, dang it!
2 units.
Worst 2 units you ever have to take. I told you that when you signed up.
Yeah.
Okay, so
Change my mind.
design a synthesis, okay? Starting with an alkyl halide and a carbonyl, each having 5 carbons or less. Okay. 5 carbons or less. Alkyl halide, carbonyl, right? So there's a couple of ways that you can do this top one. But you know I love you guys, right? You guys are great. But sometimes you whine a little bit. Sometimes you whine a little bit. I'm just saying. These are like my new adopted children that I love too, right? They don't whine.
Yes. But then when it's like the middle of the semester.
Yeah.
Wait till the first.
Okay. Okay, so how would you make that with 5 carbons or less? Well, let me just start with how do you make it, okay? In general, you need a carbonyl, right? So you could break this thing a bunch of different ways. You could break it here, here, or here. And any of those, if you just took that group off, you could leave the oxygen there and make a carbonyl. Does that make sense?
Use one of those in your Organometallic reagent.
What's that?
And one of those.
Yeah, so let's say I took, let's say I decided I'm going to deal with this one. I'm going to break it there, right? Oh, sorry, not there. There. And I can count my carbons, because the reason I'm doing that is because that gives me 5 carbons on each side of the break. So that's part of the criteria, right? So if I break it there, my carbonyl is that. That's one way to do it, right? So then that means I have a 5 carbon, like that. And then the other part will be my Grignard reagent. So this part oops, let me do it like this. That'll be the Grignard reagent. Okay, since that's my Grignard reagent, I can do, just draw it, okay? And then, oops, I'm going to put it on the other side. I hope you guys realize it's the same thing. Like that. So those are 2 parts. Now, it says design a synthesis for the following molecules starting with an alkyl halide and a carbonyl, right? Each having 5 or less carbons. I don't have my alkyl halide yet. So the alkyl halide could be that. So this is my Grignard. That's a carbonyl. And that splits it into 5 and 5, which was the criteria for the question. Okay. It's not the only way to do it, right? It's the only way to do it with 5 and 5. 5 carbons or less. You could have also, if you had done this split, split it there. You could have, for example, try to draw it right. I got too many carbons on it. See, let me just number them. 1, 2, 3, 4, 5, 6. Or you could have split it there and made it, well, I think I got too many. 1, 2, 3, 4, 5, 6. Yeah, you could have done that. And then you could have had a Grignard reagent made out of like this, what's left. Or like this, what's left. All right. So again, there's a lot of ways to do it, but that has too many carbons in it, so you can't do it that way. That's the criteria of the problem. Okay, what about this one at the bottom? All right. 5 carbons or less. So you'll notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could have a 4 and a 5. That's what that's telling me. All right. So where would I split it? So I could either split it here, here, or here, right? So if I split it to the left, then this will be what I have on the right. That's my aldehyde, right? From that. And then the alkyl halide, or the Grignard reagent, will be this. And then if I split it on the other side, again, you just split it up the same way. Your aldehyde will be on this side. And then your Grignard reagent is this. Or your alkyl halide is something like that. Okay. So just however, that one you can split a couple of different ways. Let's see, is there one that's better than the other? Not really in this case, I don't think. Yeah. Okay, questions?
If there were one that was better than the other, that could be the same.
You should try to pick the best one.
How would you be able to
Let me think about that. The carbonyls don't have as much steric hindrance, so you don't worry about that as much. So I don't know that there is a better one for this. I'm sure there's an obvious answer. I'm not thinking of it, but I don't think there is a better one for this.
I guess
If you can do an aldehydes are more reactive than ketones, so if you could do it where you have an aldehyde rather than a ketone, then aldehydes tend to be better as the carbonyl than the ketone. Yeah, I have to think about that, but generally speaking, if there's something that involves fewer steps or more efficient steps or more react, those are the kinds of things you look at. In this case, I don't think we have anything we can sort of distinguish at this point. Okay, so, I have 5 whole minutes. Right, so let's say you want to make this Grignard reagent on the left. What's wrong with that Grignard reagent? Yeah, it's got a protic functional group on it, right? It's just going to react with itself. And then all of a sudden, you're just going to have, right, this. Hang on, back up for a second. I'm going to draw that out like that. It's just going to do this. Okay? So that's not good. It's not going to be cyclic, but you'll lose the Grignard, so you won't get this effect that you're looking here to have the Grignard reagent react with the carbonyl. So there's this idea, it's called a protecting group, okay? The problem with the alcohol is it's reactive. So what you do is you put a mask over it, okay, to keep it from reacting. So think about like when you paint a window in your house. Actually, let me ask this question. Anybody ever painted a window in their house?
Like an actual, like
Actually painted anything? Actually painted a wall?
Walls around them.
Why did we call it masking tape?
to protect.
Because you mask off the areas you don't want to paint, right? Engineering, they have a mask as well, and it's for making electronics and putting traces down to create what's called a mask, so you don't get lines, traces, where you don't want them. So we use masking tape, right, to tape over the parts we don't want to paint, and then you paint carefully near the masking tape, and then you can get nice clean lines in your painting, okay? Or in electronics, you lay down a mask on a PCB board, and you can lay down lines without getting contaminating traces all over the board. So, same thing that we do here, we put a mask over here, a protecting group, on the alcohol functional group so that it no longer is protic, and then we can do the Grignard reaction. So it's pretty straightforward what we're trying to do. The only reason I say it like masking tape is because that's basically what they did here. It's like, what if you could do this? What if you could just put masking tape, protecting group here, right? And then you create the Grignard reagent, and then you run the reaction, and then you deprotect. So it's called protection and deprotection. Protecting is just taking tape and putting it down, and deprotecting is ripping the tape off, and hopefully you don't peel all the paint under the tape off, but that's a different issue. Okay. So what kind of things do we use? One of the very common protecting groups is trimethylsilyl esters, right? And very similar to TMS that we use in NMR for the reference signal, right? It's also really awesome on car windows. I will not tell you how I know this, but in graduate school, water would not stick to my windows, I would just say. Because what it does, because glass, honestly, there is actually a product for this now called Rain-X. but glass, right, has a lot of oxygen groups on it, and that's why when it rains, it wets it really well. And all you have to do is you take this same reagent, right, trimethyl silyl chloride, and you throw it on the glass, and it reacts with the OH groups on your window, and then makes them nonpolar. And so you have your whole glass of all your car windows, right, is all nonpolar now. So when you pour water off of it, it just rolls right off. We do the same thing for protecting groups, right? You take the alcohol functional group, you mix the silyl chloride here, and then you end up with this functional group. You notice this is no longer protic. So this can be converted into a Grignard reagent and be used in a Grignard reaction. Okay. Typically, what do they use for this one? Oh, they just use acid. Yeah, you can use acid to break this. Like, this is the deprotection part. So this is the protecting part. This is the protected alcohol functional group. And then to deprotect it, all you need to do, something's weird about this slide, is to add a strong acid or chloride, fluoride, bromide, those kinds of nucleophilic ions, and those will kick the TMS groups off. Okay, we'll go over those mechanisms. Yeah. I'm out of time. So we'll stop. We'll talk about protecting, deprotecting, and then we'll be done with the chapter. So the homework for this one will be due on Monday. Huh? Yeah, turn it in this week sometime. Yeah. What's that? This is 13, yeah. 12 is like 8 problems or something. 9 problems. Yeah, yeah. So what happens is when I finish the chapter, the homework's due the following Monday, but I'm not that strict about when you turn it in as long as it's in the next week. Yeah. So then I can look at it. Like these ones, I went through and I marked and answered questions. Like I asked my students, because you grade yourself, but you can get an answer and not know what's going on. You can write a question and I'll write an answer. Or if a lot of people do it, then I'll just answer it in class, right? So I like these I did on Friday to get back to people last week. Yeah. So the same thing this week. Turn it in on Wednesday. I'll go over it, and then if you're here on Friday, you can get it. Yeah, NMR license problems. Oh, sorry.